state of California. Sorry, I'm duty bound by the state of California to ask you if you consent to this video recording.
Yes, I do.
Very cool, very cool. I have here Dr. Tim Taylor, who I've had the benefit of interacting with periodically. It's a real pleasure to have you on the video cast. I think you're the fourth trailblazer actually, with regards to this new format. So thank you very much for coming on. For folks listening in or watching in, more importantly, how did you get started in this crazy thing called artificial life?
Well, that was a long time ago. I guess what first piqued my interest was a Christmas present from my mum and dad, which was a book by Richard Dawkins, The Extended Phenotype, which I read and really enjoyed, and then subsequently read a lot more of his works. But then I was also always interested in computers from when I was a young teenager. But when I went to university, I wasn't thinking of doing anything like that. I didn't even know that artificial life existed or what it was. So I ended up, I took a course where you had to study a lot of different sciences and ended up specializing in experimental psychology. But I got a bit disheartened with that and the sort of high-level models of human cognition and animal cognition that people at that stage were talking about in psychology. This was in the late 1980s, early 90s. And I was attracted to the idea of trying to build systems that exhibited some kind of intelligent behavior as a way of testing theories of psychology. And so that's what got me into artificial intelligence. And I came up to Edinburgh to do a master's in that after my degree. And whilst doing that, I did a course in genetic algorithms and gradually started to learn about this field, this was 1993. So artificial life was still quite young then, but I was starting to learn about it and starting to go to conferences. And eventually, a couple of years later, I ended up doing a PhD in artificial life with self-replicating computer programs. So yeah, a bit of a circuitous route, but generally through the idea that you can simulate and try to understand biological systems through building them in computers or hardware.
So I'm thinking of seminal books in the field. Obviously, Richard Dawkins has a few. In terms of Stephen Levy's book, did you use that at all in terms of starting to understand what artificial life was?
No, I didn't. No, and I must admit, I've never read it, and I've actually got it recently, and it's on my to-do list. In fact, what I'm currently reading, I'm trying to sort of go back and read all the books I should have read back then. I'm currently reading Complexity by Waldrop, which is I'm only on the first few chapters, but it's a very interesting background of Brian Arthur and all the people from around that time, sort of late 80s, where there was a mixture of people studying complexity science, all centered around the Santa Fe Institute.
Certainly. And they're still there, many of them, actually.
Yes, of course. And of course, that's where a lot of, that was a nexus for a lot of the early artificial life work as well. So if actually, I really love reading old books. I just tweeted about this a couple of days ago. I've just bought a copy of this for the grand sum of £1. This was a book that came up in a web search a couple of days ago, and it was published in the US in 1993. It's called The Artificial Life Playhouse. And it turns out this publishing company, the Wait Group, did a lot of this kind of, it was a series, Playhouse. So there was all sorts of other playhouses. And the idea was, it was a book for the general public. There are a few chapters on introducing the subject. And then there was a load of code, and there was a disk. You can actually see it here. There's a 5.25-inch floppy disk drive.
Wow.
And there was a load of code. So the rest of it was about allowing readers to run the code and to play about with it themselves. So it was really nice. I was just amazed. I'd never come across that before. So there you go. But yeah, I'm currently reading a lot of books from the early 90s.
Margaret A. Bowden, The Philosophy of Artificial Life.
Oh yes. That's one book I did read when I was there at the time, and in fact, I went to a workshop organised at Oxford University on. I'm not sure. I think that was before the publication of the book, so it was sort of in the lead up to the book. So there was Margaret Bowden there. Mark Beddoe, that might have been the first time I met Mark. So
wow.
Sort of a foundational figure in the field of artificial life. And lots of other people there too. So yeah, that was a really nice early meeting. So yes, that was one book I did read. That was very good.
One of the best things I did on the ARSL board was propose Margaret A. Bowden for a Lifetime Achievement Award.
Oh, yeah.
Because she's so rare that people just forget she hasn't actually received that kind of accolade from the artificial life community. It's probably the best thing I did on the ARSL board. This is a slide in my talk coming up, so we'll move that aside.
Yeah, good for you.
What I find fascinating is we had some correspondence. It's very difficult to get this gentleman to give correspondence back, but we had this correspondence with Steve Grand, and the excitement in your first email, realizing that you were emailing. How was Steve? You just met at conferences, right?
Yeah, in fact, I think I met Steve first at possibly the Biota 2 conference in Cambridge. Were you there?
No, I had a company that was willing to fly me there if I could get a ticket to the actual conference. So I was like, I can fold chairs, I can sweep if you need me. Unfortunately, both Bruce Damer and Steve Grand were kind of like the gatekeepers. I mean, when you have Douglas Adams, Richard Dawkins, when you have these people together in one place, then obviously it's very hard to get tickets. Ironically, the fellow who did The Sims, Will Wright,
oh yeah,
was a similar position. He wanted to get a ticket to Biota 2, but couldn't for whatever reason. Maybe Steve Grand thought he was a competitive influence with regards to creatures or something like that. But anyway, Will Wright and I have the same story, that we would have done anything possible to get to Biota 2, but unfortunately we missed it.
I must admit, I mean, in my naive sort of early PhD state, I didn't realize it was. I mean, it was an incredible conference, and all the people there are just amazing. Douglas Adams, Richard Dawkins. In fact, Richard Dawkins there. It was the first time I'd heard him talk about about religion and his stance, anti-religious stance, and I think it's something he talks with Douglas Adams about. But and then he went on to publish a lot and speak a lot about that afterwards. But I think the seeds of it were growing when he was at that conference. So, but yeah, that was amazing. Yeah, it just and yeah, Steve obviously, and yeah, all these people I was very, very lucky to meet. I actually one morning, so it was in this old Oxford college, Cambridge College. And so we all had breakfast together in the dining hall with like long tables like Harry Potter. And I happened to be sitting directly opposite Richard Dawkins for the breakfast one morning. And there were so many questions I wish I'd asked him. But I guess I was a bit starstruck, and I didn't really get to ask him any meaty questions. What I would have really liked to have asked him, because this was after he'd done the biomorphs and all of that, was what he thought was missing from current artificial life simulations to make them more lifelike and to give them a greater evolutionary potential. But yeah, I would have been interested to hear what he had to say about that.
Well, my talk with, ironically, Gerald de Jong initially, he told me a series of different things. He was actually at a Biota conference actually demonstrating his artificial life software to Richard Dawkins. But it was, I think he had an evening meal with him, grabbed the chat, came back the next day. I think I'm not probably telling the correct story, but basically he and Dawkins then had a jamming session around his artificial life, which just sounds like the most amazing. I mean, Chris Darby has humored me for an hour. It's like that order of magnitude, basically. Anyway, the second thing is the conversation that he did at the speech he gave at Biota. I still maintain it actively on the Biotacast site, but we call him Professor Dawkins. Let's call him Professor Dawkins. Anyway, he basically took that text and put it on his OA's webmaster did. And I had the most curious interaction, not with Dawkins himself, but one degree removed, explaining why this text had to stay on the Biota site. I actually contacted the Douglas Adams estate and I said, please take over this text. I don't, every towel day I get 60 emails just by chance. And it's something where I don't think Biota truly owns the copyright to this thing, even though he did it first and what have you. So I was talking with Gerald de Jong 3-4 weeks ago, and he said he went to a Java convention afterwards and saw Douglas Adams give exactly the same speech. So it wasn't that Biota owned the copyright to it.
Right.
It's just that Biota was the only one that maintained it.
Right.
Anyway,
yes. Yeah.
What you work on currently, which I think is fascinating, is open-ended evolution.
Yes.
And I've had the ability to interact with you thinking, this is open-ended evolution, this is open-ended. You have a very, refined definition, let's call it a refined definition, associated with open-ended evolution specifically. For the viewership, I have to stop talking the listenership. What is your definition of open evolution?
Okay.
Open-ended evolution.
I think it's useful before I start talking about that to say what it is that I'm hoping to achieve, because it's taken me a while to figure out that when I'm talking about open-endedness and when someone like Ken Stanley is talking about open-endedness, we're talking about slightly different things. So I guess in my naive state, going to artificial life conferences, I sort of assumed that everyone there, their ultimate intention was to try and create something that you would call living, a living creature on a computer or in a robot or whatever. So that's what I'm really interested in, the open-ended evolution of living beings. And that final bit, living beings, is quite important because that derives quite a lot of my perspective on open-ended evolution. Whereas Ken Stanley, and I mean, he's the figurehead, but there's a load of other people, in fact, a quite growing crowd of people interested in the more general idea of open-endedness now. And that is, I'm not saying one is better than the other, but it's a different goal. They're looking for, it's not optimization, but they're looking for solutions to problems. And so, in fact, it's looking for solutions to problems in a way that doesn't involve optimization. So they are looking for processes that keep on generating novel forms, novel solutions. But the way they do that is to introduce all sorts of extrinsic mechanisms so that they may have something that keeps a note of all of the diversity of individuals that has come up before, and then when something new appears, they measure how different it is to everything else, and if it's different enough, they'll keep it. So there's a whole load of extra housekeeping going on there, and that's all because what they're trying to do is to create novelty in terms of solving specific problems, and that's, I mean, maybe a caricature of what they're trying to do, but it's just to contrast it with what I'm trying to do, which is trying to understand how on the Earth, starting off with a physical system, which was the early Earth with no life, which is governed by physical laws. So you just have a ball of rock, some ocean, and you have all these physics, laws of physics that determine what happens to wind and rain and erosion and tectonic shifts and all of that, all driven by laws. And So the question is, and it's a philosophical question at the heart of it, also scientific question: how do you get agents, something you would call an agent, which is something that's to some extent, to a large extent, managed to divorce itself from those laws of physics and is behaving in a way that you would describe in terms of what it is trying to do, its intentions, and what it is trying to do to protect itself, to reproduce itself. So it becomes an agent following its own rules. And so that's the first question you have to try and solve. How could that possibly happen in a world where all you have is global laws of physics and a load of rock and water? So I guess so a more refined way of saying what I'm interested in is the open-ended evolution of agents, of true agents. So agents that are able to reproduce themselves and maintain themselves in an environment by extracting energy from the environment and extracting materials from the environment, and to process those for their own self-maintenance and reproduction. Okay, what I think I'm going to do, if it's okay with you, is dive right into this, and then maybe right at the end, in 10 minutes time or 15 minutes time, I might get around to answering the question what my take on open-endedness is.
Firstly, we have an open-ended time frame, so don't feel that you're time constrained with regards to this. I did a video cast just before yours, so I'm feeling at a perfect place of videocast equilibrium, and it's just a real pleasure to have the chance to chat with you. If I could throw in two questions before we get into it. Could you talk a little bit about your PhD and specifically how that gave you a particular vision with regards to artificial life? Because that, I think, in the Dr. Tim Taylor story is absolutely fascinating to me.
Yes, right. So my PhD was a system of self-reproducing computer programs. So if I take it, most listeners are probably familiar with Tierra, but I'll say a little bit about that. So that was a very famous artificial life system created by the ecologist Tom Ray in 1990. And what Tom did was to create a system where he had a computer language, a bit like an assembly language, that he'd actually written himself. And so it wasn't the native machine language, but he'd put some features into this language such that you could add mutations to a program and they weren't going to crash the whole computer, which is what would happen if you tried to do that with a native code, probably. So it was like assembly code, but a bit more robust. And
Core Wars is the basis of it, right? I think I've read the introductory Tierra paper, and I think Core Wars is like 1982 associated with this stuff.
Yes, that's right. And it goes back even further to the early 1960s.
Yes.
But so, yeah, Tom Ray, he designed a program which he would put into the memory of his virtual computer. And that program, what it did when it ran was just figured out where it started and ended in memory. And then it allocated a new block of memory and then started copying itself one instruction at a time into this new block of memory. And when it was finished, it would issue a command to spawn that new block of memory as a new program. So it had made a copy of itself. And he introduced mutations so that some of these instructions, when they ran, weren't always doing exactly what they should. So you got slightly different versions of this program emerging. And so they were competing for space because there was only a limited amount of RAM. So there was competition. So he had all the ingredients for Darwinian evolution. He had self-reproduction, inherited mutation, and competition. And he saw a load of interesting evolutionary phenomena. So at the basic level, these self-reproducing programs that he started off handwriting on, but evolution was able to optimize those. So they got shorter and shorter. So they were able to reproduce faster, fewer instructions to copy. And not only that, he saw some really short programs which intrigued him. So he studied those. It turned out they couldn't even reproduce by themselves, but what they were doing was doing the same sort of setup. So figuring out where they started and ended in memory. But when it came to the copy loop, they actually transferred their instruction pointer to a neighboring full self-replicating program. So they got a neighboring program to copy itself for them. So it didn't have to have any of the copy code. It just nicked some from a neighbor, and the neighbor obligingly copied itself. And so this virus or parasite, as it was called, was able to reproduce itself whilst being much shorter because it didn't have the copying code, but it could only do so in the presence of full self-replicators. And then there were other things. There were parasites of the parasites. So all sorts of things like that, which generated a lot of interest in the early 90s in that system. But what tended to happen was you got an initial burst of activity and some interesting things happening, but then if you left it running for a while, things settled down, and as long as you would care to run it, nothing really extraordinary was seen after that point. So initial burst of energy and then settle down to a more or less stable state. And by the way, that's pretty much what still happens with most systems. We'll talk more about that later. So my PhD was an attempt to improve upon Tierra. And the way I did it, I built this system called Cosmos, which was actually an acronym, if I can remember, for competitive, self-replicating, multicellular organisms in software. So there was multicellularity was a part of it. So I had a view of if the programs could differentiate and have different processes. So I had an idea of a model of multicellularity, sort of like how multicellular organisms develop. But rather than that, these programs would generate new threads. So they would be parallel programs with multiple threads doing different things. And I thought if you could have multiple threads doing different things and differentiating, you could get division of labor and all the benefits that involves. And maybe that would help in the evolvability of the system. They were also competing for energy. They had to actively collect sort of virtual energy pellets from the environment. And they were living in a 2D environment. So there was a whole range of things that I thought might improve the evolvability of the system. To cut to the chase, none of it really worked. I mean, I did find a few interesting features, and actually most of the things I did find were more to do with the environment. So I would introduce variation in the environment so that there were some aspects of, so it was a 2D environment. So I'd have some places which were energy rich and others which were energy poor. And I managed to see evolution of different species of organism that could cope in these different energy environments.
I have a question associated with this thing, because certainly your account and my experience for the past 28 years, slightly different. My view is that when you create artificial life, you have a responsibility. My daughters have a hamster, right? If we stop feeding and watering the hamster, we wouldn't have a hamster after a period of time. My view is that artificial life agents specifically need a variety of characteristics around them in order to thrive and, you know, in my case, create soap operas. So I think what's fascinating about your account is that you were studying artificial life at a time where the artificial life is life mantra hadn't maybe had in some regard, but the idea of creating an environment without the energy for the organisms to survive struck me very strongly with regards to your description. I like the idea of energy pellets, but it's interesting philosophically because I think I'm going to throw another curveball in here. I think the analysis of Jeffrey Ventrella, Steve Grand, is that the humans are the open-ended part associated with life simulation. And in my case, it is associated with my apes being fed and watered in most cases. Can you talk a little bit about, because I mean, this is a change in your thinking that I've only seen in recent months. Maybe you need to give your definition of open-endedness to start off with.
Okay, yeah. Okay, so, well, after all that, I don't know if I've got a succinct definition, but it involves not just the continual creation of new organisms, new species, because you could satisfy that requirement in a fixed state space where you were just going around like from one design to another. So you can do that, but it seems to me life, real biological life, has more than that. So the really interesting things in evolution are where there's something completely new and game-changing that arises. And so I'm thinking of things like the evolution of flight or the evolution of vision. So the evolution of some completely new way to interact with the environment.
Certainly. Hands are a good example. The fact that mammals have two limbs which they favor over their other two limbs.
Right. Yes. Yeah. So my idea has always been, my take on this, that you need a rich dynamics in the environment. You need a rich environment that supports all sorts of dynamics, like the transmission of radiomagnetic waves and sound, propagation, and all of that, chemical reactions, physical forces. So the question is, how do you get organisms to evolve to make use of all of that when they don't in the first place? So, for example, how do you evolve an eye when there isn't any sort of photosensitive element in the system to begin with? And so that's obviously a problem that biological life has solved, but it's a problem that is more acute when you start to design systems and software, because you really need to figure out what kind of representation you need for the environment and for the organism and for the interface between them that's going to allow for the organism to catch on to and sculpt new dynamics in the environment. So that's always been my view on this. You need a rich environment, and the question is then, how do the organisms come to use those rich dynamics for their own benefit? And this got me into a quite fundamental question. It goes back to what I was saying earlier on about how do agents arise in a system governed by physical laws. So one of my favorite examples is, just to illustrate the basic idea, is a billiard ball table. And so if you knock a ball and it will go whizzing around the table and it will knock into other balls, and there'll be all sorts of dynamics happening. But all of that is following physical laws. And so the only ways to influence what's happening and to come to different outcomes is to change the initial conditions, so the initial configuration of the balls on the table, to change the impulse you give to one ball when you hit it with your cue, or to change the shape of the table. So the table has 4 walls on each side, and so these are boundary conditions that control the what physicists might call the phase space of the system. And so there's this distinction in physical systems between the dynamic laws, which are global and act on everything and can't be changed, and these constraints and initial conditions. And I clump these all together in generally treat them all as initial conditions of the system, and that you can change. So that this is based upon my reading of Howard Patty, who I don't know if you've come across. He wrote a lot of very influential, for me anyway, very influential papers on artificial life in the 1990s. But he was primarily interested in the question in the physical world and how this process happens in real biology. But again, this concentration on the difference between the global laws and the initial conditions. So the initial conditions are what you can change. And basically Patty's view of the evolution of life is the genetic material, which is much more stable than the rest of the organism, is basically acting as a load of constraints that, when initiated by a whole chain of regulatory events, a particular gene will cause something to happen. But basically the view there is that the genome is a load of constraints which are sparking off various dynamics in the laws of physics of the world to create, first of all, molecules and higher level structures, and finally whole organisms. But it all comes back to this idea of constraints. That's where you can get control of the physics of the system. And through evolution, so the organism basically is a system with constraint closure, to use a phrase that's come up in the literature recently. Stuart Kauffman has tried to promote this idea. I forget the names of the people who came up with the idea of constraint closure, but basically an organism is something that is driven by these constraints to generate the organism, and ultimately what it does in surviving and reproducing is to create a copy of these constraints which go forward to the next generation and evolve over millennia and millions of years and billions of years. And so the view then is this: organisms today have this exquisitely evolved series of constraints, but all again, it just goes back to this basic picture of the constraints are acting on the laws of physics. And so that is where I think the path to trying to achieve this in artificial systems, particularly software systems, lies in having a dynamical system that has a whole load of rich dynamics and possibilities for interesting phenomena to happen, maybe in different modalities, light and sound and all of that. But what you're doing in evolving organisms is evolving constraints which are interacting with these dynamics in a specific way, which then loops around in an organism to regenerate those constraints for the next generation. And so that is the answer to how you get these agents with their own laws and following their own rules emerging in a physical system. It's a matter of evolving more and more complex sets of constraints on the dynamics, because that's really the only lever you have in a physical system, to evolve these constraints. And so I've done a lot of, well, I've created a few systems based upon these ideas in the past, but not very much. I've been sort of waylaid by other things in recent years, but I'm trying to come back to that, and I'm actually designing a new system now, a more complicated system than what I've done before, but still based upon these ideas of organisms as constraint-driven systems that are trying to capture dynamics that are already out there in the environment. Sorry, that was quite a lot.
No. You've perfectly characterized one of my questions, which was, what does alive mean to you? You've answered that question, thankfully.
Yes, to me, it's my view of life is quite based on biology, because that's the only real example we have to go on. But it is a system of constraints evolved in a physical system with global laws of physics that is defining itself against entropy. So I think you need an idea of entropy and decay, and the organism's fight to maintain itself, and also obtaining its own raw materials from the environment. So I think you need those things for a truly autonomous system, and then that loops around to copy and ultimately evolve its own system of constraints. And so that view of living systems is quite nice, because it inherently binds together these two aspects of living systems as autopoietic or self-generating and self-maintaining systems, and also organisms as evolutionary systems. So you need both of those for this thing to work. You need the self-maintenance to have a system that's copying the constraints, and you need the constraints to evolve so that they go from very simple beginnings to evolving much more complex capabilities. So yeah, it's all of that. It's hard to say succinctly, but I know you had a discussion a few weeks ago about Bitcoin with Gerald de Jong, about, is Bitcoin alive and is it artificial life? I didn't participate in that discussion because I find that kind of discussion just a bit meaningless, really, because it all comes down to your conception of what life is, and there's no agreement on what life is. We all have our own takes on it, and so it ultimately comes down to a question of how do you define life. And I don't think it's kind of fun as an after dinner type conversation, but I don't think you're going to get to any sort of real resolution to the question of whether Bitcoin is alive unless you all agree on what life is in the first place.
Here's my thought, specifically with regards to the Bitcoin discussion, but also in almost all artificial life simulations that have been available in the past, say, 20 years, unless the person is very anti, environment and the way you actually plot environment in artificial life systems. I think, as with Gerald's Bitcoin analogy, artificial life plus human gives an interaction where you're taking the human open-ended system and ultimately providing feedback. I think it's beautifully illustrated by Steve Grant's work, beautifully illustrated by Jeffrey Matrilla's work, beautifully illustrated by Hiroki Sayama, who we'll get to in a minute. But this idea that when you connect an artificial life system to a human who tinkers and moves things around and this kind of stuff, is this getting closer to your perspective with regards to open-ended evolution?
Yes, it is. So one of the things that I'm trying to do in my new work is to have distributed systems that will run on multiple clients around the internet, and if two people happen to be doing it at the same time, organisms can jump from one machine to another. So certainly using the internet to have a very complex environment is part of my plans. So the idea of having humans involved is also a very interesting aspect of it. It's slightly different because it goes away from my conception of trying to recreate biological life as agents evolving in a dynamical system, because you're suddenly introducing sort of godlike figures, conscious people that are external to the system and trying to interact with it and maybe move it in particular ways. But that is certainly a way to shake up the system and to try to get it to evolve different things, because that's one thing you do need for open-ended evolution. You need things to be shaken up from time to time, and so I'm thinking about ways that might happen within the system itself, but certainly having humans observing and changing aspects of the environment themselves, I think that's certainly another interesting route to take.
I mean, the simulations have to have a graphical element. They have to have something that the human becomes attached to, which is very analogous to Gerald's discussion with regards to Bitcoin, because Bitcoin has humans making it more, reproducing, making, various mutations and things happening. Let's talk about Professor Sayama's recent talk.
Yeah,
I know rewriting code, from my experience, if you take someone's existing code and rewrite it as I did, tried it in C, tried it in C++, and then found, thankfully, luckily, I had an old Mac that would actually run the original code. Can you talk a little bit about, or we can both choose to talk about evolutionary swarm chemistry specifically. Yeah. It does have the E word in it. What are I think your views might have changed in recent weeks, or maybe they're just even more emphasized. Can we talk a little bit about that?
So, to start off by saying it's really lovely work, and I think it's fantastic. For me, it's possibly demonstrating open-endedness in this wider notion of open-endedness, but not necessarily open-ended evolution of living systems. So you get these interesting self-organizing dynamics emerging. I actually played around with that sort of system in the early 2000s, where you had a physical system with different particles where you could control the amount of attraction between them. I didn't publish anything. Hiroki's done infinitely more than I ever did. But that's to say, I think it's a very interesting and fruitful area to be looking at. And all sorts of things like this, and we might bring linear into this as well, are really interesting collective dynamics and self-organizing dynamics. But I'm just not quite sure where the organism is. So for me, just to re-emphasize, I'm not disrespecting the work at all. It's just from my perspective of evolving life, these things aren't living, because from what I've seen, what you tend to get is clumps, maybe not perfectly circular, but you get some aggregations of particles. They may all be of one type, or they may be of 2 or 3 different types. But if they're 2 or 3 different types, there's nothing holding them together, as it were, or specifically trying to regenerate that specific pattern. It's just how the dynamics work out. So each of these particles has a genome which controls how it interacts with other particles.
It's a variable length genome as well,
yes.
Which I think was one of the things that initially drew me to the work as a potential. I think the increasing complexity that you need to have in an open-ended system is potentially something that you could track. Hiroki's 2018 work says basically, and I found this with the simulation as well, that basically, I don't know what thousandth mark it is of iterations. You set off, firstly, to describe it for the listeners, you set off with some initial conditions, which are also of any length. And through that, you get very lockstep, movement to certainly a collection of entities that look very cellular in nature, may have internal. But I think it's interesting because as it fits into artificial chemistry, which obviously I've talked about pretty well ad nauseum in the prior bioticasts with people like Dr. Bruce Damer, that that is, for me, fundamentally fascinating. And it's also what Hiroki keys off in the 2018 writing. That these initial conditions that produce these things, you kind of have a series of images and you say that one or that one, and they have an underlining startup, strings, for want of a better term. It was interesting to me because having gone through the code and having had to rewrite the code and have a broader understanding, I thought this is what's really fascinating here is that Hiroki published this work in 2011. The movement from 2011 to 2018, no change in the software, just studying it for an extended period of time, which I think is a metaphor for a lot of artificial life developers as well.
Yes.
Once you get involved with your simulation, the fascination of fixation on it enables you to see things that weren't originally there, which I thought was particularly beautiful in Hiroki's work. So I think there's the potential here for a number of artificial life simulations to either be built on this or very similar to the cellular automata. Cellular automata haven't been the same thing always. There have been various evolutions captured in the likes of Golly and various other cellular automata simulations. So I think Hiroki's perspective, it appears, he didn't actually state this explicitly in the video that's recently come out, but my view is through his studies, he's getting to open-ended evolution as something that he described. Your requirement for being alive, I think, is a very interesting one, which I don't know. How do you see it being satisfied? Do you think your new work will be alive?
Well, certainly in my new work, I'm trying to base the organism upon something that is an idea that it's an organization of components where each component is doing something that's required for the whole organism to reproduce. So there's a solar panel for collecting energy, there's a battery, there's a mouth, a storage of sort of a stomach, there's a genetic component and a something that will read that and create an adult organism. But the thing is that all of these things are having to work together as a machine in order to, first of all, survive. So they're moving around the environment, having to collect energy, having to collect materials. So there's conservation of matter and conservation of energy. They may break materials down and then sort of recombine them if they need different kinds of matter. So there's all of this going on. So it combines an idea of an agent as an ecological, self-maintaining, or autonomous agent, and also, again, a reproducing agent. So that's what I'm trying to do. And I mean, so what I would like is to understand, well, I don't know if Hiroki is trying to evolve living things specifically. If he is, I would like to hear what his definition of living things is. So for one thing I really like about swarm chemistry is that it is all of these particles have their genomes, and these evolve over time, and so this is kind of evolving constraints for the dynamics of the system, which, as I talked about before, it's just that an individual particle has a genome, but there's no genome specifying a whole higher level structure. That comes about through the dynamics of the system and the self-organization of swarm chemistry. But the genome doesn't specify a whole organism, and so a whole organism doesn't reproduce as a whole. So yeah, it just seems and actually even the individual particles when two particles collide, there are these rules which seem a little abstract to me in terms of it. It depends on how you've configured the system, whether to determine which of the two genomes gets copied. It may be the one which is traveling faster, or there's a short list, as I'm sure you've seen. So, but that seems a little abstract and not really having any corresponding process in nature, as far as I can see. So again, I'm not saying anything bad. I really love the work, and I love the dynamics and the ability to create all these very interesting organizations. And I think that kind of work is very useful, because as we go forward in artificial life, following my vision of having very complex dynamics in the environment and trying to evolve to make use of those dynamics, we need to have lots of different worlds, lots of different environments with interesting dynamics, and so swarm chemistry is exactly that kind of world. It's a world with interesting dynamics, and I think there's a lot more you could do there.
Certainly. I think that's the beauty of the work, that basically you have source code that was written in 2011 in Java, particularly obscure source code, unfortunately, as I tried to make it more mainstream in my conversions. But no, I'm going to have the luxury of actually having Hiroki on a future video cast. So I'll be able to talk with him directly about this.
Yeah.
Certainly his presentation didn't get as deep as I wanted him to get. It was one of those situations. I could have had the option of actually writing questions, because I watched a large portion of it live. But then I thought, no, my questions will perturb it. I wanted to see Hiroki naturally in his own element with regards to what he was presenting, with the view that he can be perturbed in this video cast if need be. But yes, I think it's an open question to, make a point. I think it requires, certainly from your experience, something that's slightly more robust. And I think the interesting thing that I found about his work was, with artificial chemistry, you are able to write your own rules of physics fundamentally, and
Yes.
that's a large portion of the work associated with that. So I wasn't necessarily as turned off with regards to his own particular physics through it. I think it needs to be abstracted and discussed independently. But it's wonderful just to have this work kind of, for want of a better term, evolving, but actually being more mature and associated with the people that are studying it. And I think that's a history of all artificial life simulation. Tom Ray's Tierra. I've had the luxury of talking to Tom Ray. I had a bunch of students in the audio chat while I was doing that. It's interesting, actually. Ken Stanley as well, I've had the opportunity to chat with. And one of the luxuries with regards to the Biotacast, which has now become Last Monkey Standing, is just these open-ended conversations, which enable us to move in different directions. I'm feeling that you should probably come back on, or maybe even I could challenge, I don't want to use the word challenge, even maybe you could sit in on my discussion with Hiroki, because I think the two of you together would provide a gestalt which is probably better than the sum of the parts.
I would love to. Yeah. If Hiroki's up for that, that would be fantastic.
Well, Dr. Tim, thank you very much for your time today. It's been an absolute pleasure. Don't be a stranger. My view is, as these conversations evolve, and you've given me good candor associated with the previous conversations being interesting to you, let's have you back on, maybe before or after, maybe with Hiroki specifically. But I'm really interested in your changing perspective. I dare not say it, but your changing perspective, as I see it at least, from kind of definitional work as it moves through. And I think the next book of yours, I hope will, I don't know, I feel that Stephen Levy's work has never actually been achieved again. Chris Adami's work is a little bit like that. But what I got out of Stephen Levy's work was a friendship with Larry Yeager, which I never would have had otherwise.
Right.
So I think there's a need for the wiki on the International Society for Artificial Life. That's a good project in and of itself, but there's a distinction with that in a book. And maybe I'm just showing my age that books are actually, we should be doing video casts. That's probably the better way to reach the audience. So anyway, time will tell.
Yeah, I think, I mean, actually, I really love these video casts, and it was a surprise to me, because I was I was enjoying the podcast and I'm listening to a lot of podcasts, but I think I enjoy the videos even more because, yeah, just they're just, I don't know, more engaging.
Well, you get to see people's faces. You get to see
Exactly.
the animation of the discussion, which I think is such a large part of Artificial Life, just in terms of the excitement that people have creating simulations, talking about their simulations, talking about other people's simulations. It's all this wonderful tapestry, which I'm now capturing on video.
Absolutely. And thank you very much for doing it. Keep up the good work, Tom.
Well, thank you. Thank you, Dr. Tim. It's been a pleasure as always.
Okay. Thank you. And I'd love to come back some other time. So.